what it is, what's IoT actually? There are diverse types of definitions, or what is the meaning of IoT. By default, it is a device connected to internet and network. Here, I'm saying device without referring if it is a tiny computer, is it a tiny device, is it an electronic device, but a device which has capabilities to be connected on internet. It can be a cup, it can be a bottle or whatever it is, but it is a device which has capabilities to communicate with other devices over internet. Why do we want to connect everything? Why do we want to connect even the tiniest devices in the world on internet? And the answer is quite easy, because we would like to have remote control of them. For example, if we would like to see what happens at our home, we would like to have IoT enabled, let's say oven, and then remotely you will enable the oven to start heating or start preparing any kind of meal or any kind of tea or whatever it is already placed on the oven. We would like to also do data acquisition and analysis remotely. For example, if we are to see what happens with our ship, we would like to have capabilities to remotely activate system which will do data acquisition from our ship, and then we will get raw data and process it remotely at our system and get results based on the acquired data which are done remotely. We would like also to push some information from internet. For example, at home, we may want to have a small screen on which we display different types of images, and sometimes we would like to put information from outside to that screen so we can get information exposed in our homes, and the push of information will happen from internet. Something similar is if we would like to use some additional broad range of internet services. For example, we may have an oven which is internet connected, and the oven may have capabilities to get recipes and expose details which are coming from internet. Sometimes you may also use your oven if it is a smart oven, and then you can say, okay, I would like to have potatoes cooked for today. Give me proposals of recipes how I can cook the potatoes. Then the oven, which is smart, will get information from internet about different types of recipes and will help us in cooking something new, or to cook the potatoes in old-fashioned ways, but based on the recipes taken from internet. Which devices can be connected? As I initially said, the goal is to have everything, any device or any asset connected. Example devices are white goods, as I said, oven, refrigerator, or whatever it is that we have at our homes. Body monitors, especially for the persons who may have some health issues, they may have devices which are attached on their bodies, gathering information about the blood pressure, temperature of the skin, oxidation of blood based on sensors, and expose all that information on a doctor or a physician which is capable of analyzing the data about the state of your body and proposing maybe some activities that you may have to take. Air conditioning, for example, if you go home and if you would like to have air-conditioned room prior you go home, then you may remotely set what is the temperature that you would like to have at your home, and prior you reach your home, everything will be prepared. So whenever you go at your home, you will not experience high temperatures or low temperatures because the weather is not proper. And it is a countless number of places where you can connect your devices to internet and see what is happening. One of the simple things would be if you have a refrigerator and you have no idea how many eggs you have inside. If you have an internet connected refrigerator with a camera inside, then you can enable the camera on your way home and see how many eggs do you have, or maybe if you need some other groceries in order to buy them on your way home. Then the next question about IoT is why IoT is blooming now. Maybe not now, but starting from 2015, we see that there are more and more devices which are internet connected. And if we think why recently the IoT is blooming, based on some analysis that we did, is because the cost of technology is lowered and the maintenance is also lowered, which means that in the past you may have to pay like, I don't know, 50 euros monthly for getting internet connection with a limited bandwidth, but today you can pay 30 euros and get much better service, and then you have higher bandwidth of internet that you can utilize not only for surfing or downloading files, but you can use it for streaming videos out of your home, so you can see what happens at your home on your mobile phone. So you have lower cost of all those devices which are internet connected, plus the monthly costs that you have to pay in order to have your home internet connected are much lower compared to the past years. And also, market needs commodity. We are getting a little bit more spoiled as the time goes, so we would like to get extra services and utilize them in the best way possible. So what happens when we connect a device on internet? It is extremely important that device acts predictable or safe, meaning that if you are to turn your oven on and off, you have to be certain that that happens always predictably, and there are no scenarios in which the oven is turned on for 24 hours on maximum power, which will in many cases introduce a fire or will damage the oven that you may have at home. We have to also expect that the devices provide only functionalities for which the system is designed to, meaning that if it is a light, it has to act as a light only, meaning that it does not have to be designed to radiate some RF energy or do some stupid things because it is malfunctioning. So primarily it has to work for the things for which the system is designed and be predictable and safe. It has to be secure, because in many cases the devices will be capable of exposing your private data, and therefore the IoT devices has to grant access only to users with proper credentials, limit information exposure, and avoid device misuse. When I say grant access only to users with proper credentials, means that the system has to be capable of authenticating that the person trying to gain access to the device, that he has a proper credentials in order to see what is the state of a device and maybe enable video surveillance or see what happens in the area in which the device is installed. It has to limit information exposure. For example, if there is a camera at your home, you have to be certain that the camera is not, the device is not exposing information from the camera to unauthorized persons. It is not only about the camera, it may also expose information, are you at home or not, meaning that the burglar will know if you are at home or not and attempt to enter within your home. Something similar goes with avoidance of device misuse. For example, there are many cases in which internet-connected devices were with a malicious operating system on which it was possible to install, for example, mail servers which are pushing a lot of spam mails throughout the devices. For example, imagine that there are, for example, 1 million routers who are with a malicious software installed, and all those 1 million devices can be used for introducing denial of service attacks or maybe mail spamming throughout the world, dictated from one place. And of course, you don't want your device to tweet what's your weight if you're not satisfied with the weight. Okay, so let's speak a little bit more about security. What does it mean as a principle, or how the security might be implemented in digital systems? So the basic question is what security is, or what the security mechanisms are. It is a set of complex mechanisms which are granting limited access to a secret. One of the oldest devices is CryptoBox, in which you have to put a correct order of letters and then you will gain access to the secret inside. And there were two types of devices, which one of them is actually granting access or not within the secret which is inside, and the other ones are if you miss proper combination, then there is some kind of liquid flowing inside which is destroying the information which is concealed within the container. So in basics, it is a set of complex mechanisms which are used in order to grant or forbid access to a secret which is concealed inside. How? It will have to provide protection from generic and advanced attacks, and it will have to use diverse methods to achieve required level of protection. Whenever we design something, we have to define the level of protection which is expected out of the device. So whenever the device mechanisms are designed, they will be capable of coping with the expected methods of attack. How to use it? So how to use the security does not matter. It has to be very easy to be used, because if the security mechanisms are quite complex, then people will start to misuse it or will not use the complex security mechanisms at all. I will speak a little bit later on about it, and we will get more details about what I think about this. And then the interface has to be compliant with the target users. For example, if this device is meant for blind people, it has to have completely different interface for communication between the device and the user. If it is maybe for some other type of persons, then the interface has to be designed completely different. So we have to take care about the interface as well. What are the common mistakes that I have seen in the past? It is sometimes if the security is too complex, or it is extremely complex to gain access to a security, then, for example, if you have a box and you have to lock 12 locks in order to gain access to a secret, and you have to do it like 3 times a day, at the beginning you might not be so lazy and you will lock all the 12 locks, but as the time goes you will lock only 1 lock, which means that if the security mechanisms are so complex, then you will not use full set of mechanisms, but you will start using only subset of those mechanisms, which are significantly lowering the security. Even though you may have the most secure system in the world, if it is not used properly, then the security level will be quite lower. And in many cases, we believe that obscurity is a security, meaning that if I cloud information about my system, I will believe that other people are so stupid that they will not identify that I'm clouding the solution. So it's not a solution actually, meaning that in order to have a proper security mechanism, the mechanisms have to be open, and the complete security should rely only on one secret. So we will speak later on about it. Do not try to obscure things and believe that people around us are stupid and they will not notify that it is just an obscurity around the mechanisms. In many cases, we are not aware about the threats. So when we establish a security mechanism, we have to take care about all the aspects and all the possible ways how our system will be attacked. Because the weakest link in the chain is the one which is usually broken, meaning that whenever we make a system, we have to think about all the details and about all the links within our system. Same goes with analysis of what kind of vector attacks are used in order to break our solution. So we have to be very proactive in thinking how the others may misuse our system, and think that not only the ways we think are the only ways in which the system will be misused or attempted to be broken. So collaborate with other people and understand first what would be the most common and advanced attack methods which will be used on our system. If we speak a little bit about information security aspects, what are the things that has to be designed or added within our system in order to have a better protection, especially in digital systems? It is we have to introduce a mechanism for detecting of tamper detection or protection, meaning that first the system has to do a kind of a self-check, so the system knows if it is tampered or not. Because if the system is tampered, then it is much more easier to break it. Therefore, the system has to have a mechanism to do a self-check prior it continues with the next step, or prior giving a possibility to gain access to the secrets concealed within the system. This mechanism will have to guarantee that the system elements are not modified, and within embedded systems, those mechanisms rely both on hardware and software. The idea is to have both hardware and software involved in verifying that the tampering of the system is not happening and that the system is working according to the original specification. Then the next thing is authentication. We have to get confirmation that there are possibilities to securely verify all the requests for system access, meaning that whenever we try to gain access, there have to be a mechanism which is verifying that all the requests are secure and that we can make a secure verification of all the requests. Then the system will also have to provide mechanisms which are giving different levels of access depending on the credentials which are exposed. This means that maybe you would like to grant access for someone just to the entrance to your home, but not getting into the bedrooms or living rooms, or for rest of the people or the people living within your house or your home, you would like to grant full access. Something similar is, for example, if you have a Linux system or Windows, there are people who are using the systems and they are normal users, but they do not have the credentials to modify how the system behaves, and there are also administrators who have a complete access to the system, and they can both use the system and modify the system so the others can use it in a different way. Also, there have to be mechanisms for data verification and encryption, which verification guarantees that the message is not altered from the origination point. So, which means that if I make a message and I hand it over to you, there have to be a mechanism which will verify for you that the message is actually originating from me. Why? Because there can be someone else pretending to be me and giving you a message in my name. Therefore, the security mechanisms have to guarantee that the message is also coming from a trusted source, or it is coming from the person who is pretending to be. In many cases, we can also introduce encryption, in which the original message is encrypted in a format which is difficult to be understood without proper decryption. And in many cases, all the data verification and encryption is done by using private key infrastructure algorithms, in which the message is encrypted with one key, but it is decrypted with another key, meaning that there have to be a pair of private and public keys which is used by both sides. And both sides have two different keys which are used for encryption and decryption of data. The same keys can be also used for adding digital signature on top of the message, which will be used for verification that throughout the path the message was not tampered or changed without proper authentication. So let's continue to discuss a little bit more about the security in modern digital systems. So basic principles, as we said, we have to ensure that we trust the system. So when the system is powered up, it has to do self-checkup, which will show if the system was tampered while it was in a shutdown state. Also, the next step is the system has to ensure that the secrets are not tampered, meaning that there were no changes of the keys which were embedded within the embedded systems. And we have to be certain that we rely on mechanisms which are not tampered. And we will have to rely on secrecy of keys, because we have already verified that the keys are not tampered. However, not only during the system startup, the system will have to continuously monitor what happens with the systems, and if there are attempts to tamper the system while it is up and running. Meaning that when the system is powered up, you do a self-check, but that is not sufficient in most of the cases. There have been a lot of situations in which after the system was powered up, there were attempts to tamper with the keys or with the systems which are used for encryption, decryption, or providing basic security mechanisms within an embedded system. So there have to be a constant monitoring what happens with the system. We spoke about the basic security mechanisms. I will go a little bit more deeper within the embedded systems, in which we use, in many cases, verification of the executables, meaning that one of the steps in which we are verifying that the system is working properly. After the hardware is initialized and verified, the next step is to verify that all the executables and all the configuration files are intact and guarantee that they were not modified while the system was shut down. We do that by creation of a secure boot, which is based on a well-defined chain of trust. And then that one is guaranteeing a low risk of tampering of secure mechanisms, which are mostly implemented within software. As you may imagine, some components of the security mechanisms are implemented within the software, and the only way to verify that the software was not tampered was to verify the digital signature put on the software prior it was written into the flash, and that one is guaranteeing that the software is coming from a trusted source. The systems in which we work mostly, we verify all the executables. Actually, we verify all the software prior it is executed. So there is a step in which we first verify if the software is genuine. If it is not, then the booting is not working, is not continuing, and the system is hanging up. And the same goes on a step-by-step boot loading, in which the system is verifying everything prior it is executed. And that goes for all the software within the system. We also have to do protection of a sensitive data, key protection. In many cases, keys are protected within the OTP or ROM area, which are hardware-based, but there are mechanisms in which you can also put keys within RAM, which is either tamper protected, or RAM, which is quickly erasable if the system is detecting attempts to tamper with the hardware. We can speak a little bit later on about it. So as I said, sometimes we would like to destroy the secret. In some cases, we would like to conceal it and not granting access to the secret. So we protect keys, private data, and data partitioning and separation, meaning that in many cases we are also protecting pointers showing how the data is partitioned, because if you tamper with partitions, then you may also put the system in undefined state, which is initial state in which the hackers are entering into a backdoor or putting the system in undefined state. We use also quite a lot of operating system features in which processes are separated or sandboxed, and then we introduce quite a lot of kernel security mechanisms which are needed in order to utilize the hardware and software components in the best way forward. So I spoke a little bit about defined chain of trust. Everything begins by defining or putting anchor of trust. And I would like to speak a little bit about it. What does it mean? It is an entity to which the system has an ultimate trust for truth, meaning that that's a component in which we trust without any doubts. So in many cases, it is quite difficult to define what is a proper anchor of trust, but in many cases, it is sufficient to have it embedded within a hardware, within a secure ROM, which is, as you all know, read-only memory, which is programmed once, and there are no methods to easily modify it, and therefore we believe that on a system, the secure ROM, which is part of the system-on-chip device, is an anchor of trust, because that one is not easily modifiable. Or if it is modified, then it is easy to detect that there were tampering of ROM code, which will make the system hanging and not continuing to boot properly and expose data whenever later on the system is up and running. So we rely on secure ROM, OTP configuration. It is a tiny area of memory, which is one-time programmable memory. And in many cases, we put keys and configuration data within the OTP, saying how the system should behave and what kind of security mechanisms has to be enabled and how to utilize them. So whenever we write a configuration, we believe that when configuration is written, then there are no easy ways how to change it and misuse the complete system afterwards. And then there is there are many complex hardware modules which are later on utilized by software, providing more details and more mechanisms to verify that there are no changes. In this sense, using those hardware modules, which are part of a so-called crypto engine, are used to do encryption and decryption of data by using the information from the OTP configuration. There are also a set of functionalities which are embedded within the ROM routines, and they are utilized throughout the booting process mostly, and in some cases even the operating system is using some of the ROM codes in order to gain access to a piece of memory which cannot be easily changed. There are complex verification mechanisms of hardware state, of health, meaning that even though, as I said, we began by doing self-check throughout each and every step of booting process and then execution of each and every application, especially whenever we are utilizing some of the secure functionalities, the system is constantly checking what is the hardware state and if there was an attempt to do any modification of the hardware. Keys are always protected from direct access, meaning that there are no mechanisms which the user application can use in order to gain access to the keys, meaning that you cannot write an application in modern operating system in which you may say, okay, give me the master key out of OTP. Those operations are not allowed, meaning that you may request a service like verify if this digital signature is proper or not by using key number 1, and then the below services will gain access to the keys, verify of the piece of binary that we provide, and then we will get only result back as an information if the process or if the operation was successful. The secure domains or secure hardware components are always available from trusted domains, and in many cases we rely on secure ROM code. Buffers used by the ROM code are also strictly protected. I will show an image later on that in many cases the ROM code is also, as you may imagine, an executable, but all the variables have to be placed in some kind of random access memory, and that random access memory and all the buffers has to be also properly protected throughout the boot process and whenever we would like to use secure ROM functions. This means that even though there is everything is put in read-only memory, there is a tiny piece of memory which is RAM used for storage of all the variables and all the buffers, which has to be properly protected in order to have proper execution of ROM code functions. So we use actually in order to gain proper anchor of trust, we propagate all the information through protection mechanisms like MMU, bus firewalls, bus gateways, and all of them are configured in a way that we would like to have in order to guarantee that all the data flows in a proper direction and that only limited access is given to the resources within the system. Then we are guaranteeing seamlessness of execution regardless of the state of the rest of the systems, meaning that if there is a need to gain access to a specific key, all the gateways are set in a way that only the trusted applications can gain access to those specific areas. And those gateways are seamless for the secure application. But if unsecure application would like to try to gain access to the keys, then the gateways will prevent it and all the accesses will be forbidden for untrusted applications. And once again, active self-monitoring, we cannot say that now we are safe and we do not monitor anything afterwards. All the time we have to verify that the system is running according to the original specification and that there were no attempts or no possible breaches of the systems while the system was up and running. I spoke that one of the things is secure boot, which is starting from the when the system is powered up, and this is like, as I said, it is the anchor of trust in which we say that we are creating a chain of trust starting from booting up the system until each operating system is up and running by verifying each and every piece of code which is loaded and then executed. So we have to do, as I said, verification of executables, the executable is bind with a small header giving information about the type of the executable and type of digital signature, which is bind at sometimes at the end, sometimes at the beginning of a blob. And then those signatures are always designed, actually created, in order to be verified with the secret keys which rely inside of the OTP or inside of the hardware of the platform which is booting. Sometimes binary is also encrypted, especially if it is a small bootloader which may reveal details about the hardware. Then it is safe to also encrypt the binary, so it is much more difficult to do reverse engineering based on analysis of the code on the executable. Mechanisms used, once again, anchor of trust is set in ROM. Actually, all the keys are placed in OTP, and then whenever the platform is started, the ROM code functions for verification are reading the binary, passing the header, and based on the information within the header, they are calculating and verifying the signature, which is at the end of the binary. If all the things are set properly and the signature is correct, then the ROM code will execute the application and will move with the execution of the next step. OTP is used for storage of the keys, and in all those activities we utilize both hardware and software to maximize robustness, because it is proven that if we rely too much on hardware, then we may have problems to get rich diversity of functionalities, because hardware is always limited what kind of functionalities can be provided, but then we accompany that one, or we complement that one with software features, and both of them guarantee wide portfolio of functionalities that can be used, and security which is on a level in order to guarantee that the executables are verified prior they are executed, and that all the signatures are in place and proper. When the operating system or the main application is running, all the sensitive data is verified prior it is used, and then the sensitive data can be system configuration, data configurations on specific applications, information how the firewalls are to be configured, how to provide access to the system for different people, or what are the credentials that can be used, and all that data has to be properly verified that it was not tampered and it is valid to be used by the system after the kernel is up and running. All the additional software is verified prior executed, meaning that we do not verify only the kernel and the system things, but we also verify the applications which are to be executed afterwards. And once again, frequent verification of the system for tampering. So we should not forget that we have to constantly monitor what is happening within the system, because on a live system there will be a lot of attempts to hack the system and remove the protection mechanisms. How does the standard secure boot looks like? You power up the hardware. What you have is internal SRAM, which is limited, not at 8K, but in the old days it was quite limited on 8K. And then the system, as I said, will do initial verification if the hardware is in a proper state, and then the ROM code will start with booting. We'll check what kind of memory is attached to the microcontroller, and we'll seek for the pre-bootloader stage. When the pre-bootloader stage is identified, then the ROM code will start with its initialization and loading of pre-bootloader, which is small enough to fit into the available area of static RAM, which is embedded within the microcontroller. Then when the pre-bootloader is loaded, it is executed. And then the pre-bootloader has the capabilities to initialize the big external memory, in which the pre-bootloader will start loading the bootloader stage. Of course, I forgot to once again mention that whenever something is about to be loaded, first if it is verified if it is tampered or not. If it is tampered, then the booting process stops. If the bootloader is not tampered, then the system loads that component, stores it into the RAM, and executes. The bootloader, whenever it is executing, it is getting a little bit more space in order to put all the stack, all the heap, and all the additional variables which are needed. So until now, the system is starting in a privilege mode, meaning that those pieces of code are verified, they are trusted, and they can gain access to everything. But when prior we start loading the rich operating system, in which we do not have capabilities, or we don't want to grant capabilities to gain access to everything, we start with separation or partitioning, and then we initialize one piece of the memory to be for the untrusted or normal execution environment. And then in that one, prior we continue loading the rest of the components, we take from the file system, trusted execution environment operating system or microkernel, which is verified and executing into the trusted environment. Then the next step is to start loading, verifying the kernel, loading that one. If kernel is properly verified, then it is executed. And then we have all the applications which are, of course, verified prior they are put in memory and executed. After the boot loading process, we have a setup like this, in which we still have a piece of code here reserved for the boot ROM code. We may keep some functionalities of the bootloader, but by default we always have to have the trusted execution environment operating system running in privileged mode, which has access to everything. In unprivileged piece of the memory, we have Linux kernel and all the applications which are running in that environment. What are the operating system's features which are needed and used? So we have to utilize all the hardware modules for protection, memory management unit, memory protection unit, system control devices, bus interconnect features, all the gateways, and all the firewalls. And that one is crafted to ease use of complex IP blocks. For example, if we are to play multimedia file, we don't want to know everything about the multimedia decompressing devices, but we would like to just get a stream, push it through a proper device driver, which is in many cases given by the operating systems, and then you watch the video on your screen. If needed, the operating system can also introduce virtualization in order to provide proper isolation between two or more operating systems or two or more environments in which the applications or operating systems are executing. Use of advanced operating process threat isolation mechanisms in order to guarantee that whenever one process dies or behaves unpredictably, the rest of the system will continue working properly. Confinement of secure services in as small footprint as possible. It means that we would like to, in a rich operating system, you have large amounts of code, and it is quite difficult to secure that each and every code is working properly or secure. The modern security principles apply that you gather all the security mechanisms in as tiny area as possible, put a lot of effort to verify that tiny part of software code, and rely completely on that one, and trust that the execution of that code is always according to the specification and it is trusted. I'll speak a little bit more about it, but the idea is, as I said, you have Linux operating system with a lot of features, but you cannot simply verify everything. You cannot verify everything, and therefore the idea is that the secure features are concealed in a small footprint and kept and run in a privileged mode, and they can gain access to all the security features on the hardware. So we are running out of time, so I'll skip some of the slides. As I said, in privilege mode, there are also two areas, user and privilege trusted execution mode. Here we have all the applications which may gain access to secure hardware, but from this area we have a very strict split, meaning that if you are to gain access to system for doing some decryption, you cannot simply go directly, but you have to request services from the applications which are running in trusted execution environment, and they can, through the layers of the trusted execution environment privilege mode, gain access to hardware which is secure, and this mechanism is guaranteeing that a bad application over here cannot easily tamper with all the hardware and all the applications running in this area. Protection of sensitive data, keys and certificates. We spoke pointers to diverse type of partitions and data, configuration data, user data and secrets. I would guess that nobody of you would like to have a system which is exposing private data like bank accounts, information about your balances, your behaviors. Therefore, we have to conceal them in a tiny area. And we use a lot of complex mechanisms which will keep key data and user data in a specifically crafted secure monitor device which has tamper detection sensors, meaning that if an application from here would like to gain access to some of your security data, it will have to pass through different layers of verification which verify if the request for access is coming from a valid application, if that information is available for exposure outside of this secure monitor. This is a device in which there are sensors which are also detecting if, for example, we have a point of sales terminal. If you would like to open the point of sales terminal and gain access to do analysis of all the certificates and all the information inside, those sensors will inform this tiny piece of hardware, and then quickly, when the box is opened, all the certificates and all the secure data will be erased. So this is a mechanism in which we quickly erase all the secrets inside of the box, which there is a tamper attack detected. This is one of the IoT devices that was designed by us. We've been using proven industrial Q or IQ platform coming from Freescale or NXP or Qualcomm today. It is equipped with state-of-the-art hardware security modules. They have a lot of mechanisms for concealing, protecting data. They have also advanced hardware crypto block, which can do a lot of execution of crypto algorithms within hardware, which are offloading the main CPU from cryptography functions and giving more room for the application more room for the main CPUs to execute the applications running on the system. We are using extended system partitioning mechanism in which we put kernel, device tree, root file system, home folder, and everything in a different partitions. So we have a very strict mechanism how we verify each and every piece of code prior it is executed and given access and granted access to the secure blocks within the platform. The platform is highly integrated and diverse. It has extended set of interfaces for networking. Actually, the idea is to have in one box IoT Gateway with 6 Ethernet ports plus advanced routing functionalities and capabilities to add Wi-Fi function. And on top of this kind of gateway and router, you can put home automation system, which can be used for controlling of your devices at home. So in one box, you have IoT Gateway, router, plus home automation system, which can be used for communication with external modules, which can control activation of lights, activation of heating, or activation of some additional slaves. At the beginning, we've been using off-the-shelf components, which are pre-configured for security. Communication is over power line interface. The installed operating system and software is we are using custom created Linux distribution based on Yocto, in which we have enablement of all the security monitor functionalities, which are part of the platform. We are using custom-designed OpenSSL, which are not using software implementation of crypto algorithms, but OpenSSL crypto is using dedicated hardware for implementation of OpenSSL functionalities like AES encryption, RSA encryption, and IPsec encryptions needed for transferring data over a secure line coming out of the Ethernet. We've been using applications which are developed to use all the hardware accelerators and system support mechanisms, meaning that whenever we attach a camera to this device, the camera is utilizing all the hardware components for fetching the data, doing encryption of camera data, and then pushing it over Ethernet connections outside on Internet or toward another device. Overall security architecture, gateway, it is fully secured. It is using, of course, secure boot to verify each and every piece of code prior it is executed. We are using hardened operating system in which we are removing all the services which are not needed, but we left only things which are needed for the use case that we have. Network stack is configured for limited access, so we did heavy changes into the IP stack, how it is behaving. Encryption enabled on all data transferred toward the Internet, meaning that whenever we enable any kind of data transfer, it is going over encrypted packets. Strong authentication scheme introduced in order to do verification what are the credentials of every users that would like to gain access to the system, and the authentication goes on two levels. One is on system level, meaning that we have a set of users which are verified by the operating system, and the application that we have on top for control of the devices has another scheme of user access, meaning that by default, whenever you would like to log in and control your home, you have one level of access, but if you would like to gain access to the system and do modification on a system level, then we have another set of authentication mechanisms or authentication schemes introduced. As I said, hardware crypto acceleration and encrypted communication with all the slaves, because as you see, if we connect on a power line, a socket over here has pretty much the same connection with the socket into the other room, but the idea was to have only communication with the slaves, which are approved and they have proper encryption mechanisms introduced within themselves as well. So the slaves, they have to be very simple, therefore we introduced basic security in them. They still have the secure booting, of course, but they do not have all the complex mechanisms with rich operating system and separation of different modes. Actually, there are no privileged and unprivileged modes. Everything is within the privileged modes, but all the communication goes only with authenticated gateways. It is encrypted communication, and the idea is, as I said, they have to be super simple, so they're quite cheap, and you can even have Wi-Fi enabled light bulbs, which are also communicating with the gateway via encrypted line. So the idea here is to be capable of plugging in a device in a socket which is properly configured. Device is doing credential exchange with the slave, and whenever they authenticate themselves, then this slave can be part of the network, and this slave can be controlled by the gateway over here. If the slave is not properly configured, there is no proper authentication between both of them, and then the slave is ignored and all the communication with that one is shut down quickly. I am a little bit off. So, thank you for your attention.